welcome everyone to the tutorial on advancing data selection for foundation models from heuristics to principled methods. I'm Ludwig, I'm an assistant professor at Stanford, and today, together with Ruoxi and Tianhao, we are going to tell you about the state of the art in data selection, especially with a focus on training foundation models. Cool, so let's get started right away. We have a lot to talk about. And yeah, I don't think I need to motivate to anyone here in the room, we are at NeurIPS, that AI is super important, has been a super exciting field to be in now for more than 10 years, and since ChatGPT and the rise of language models, it's just getting more and more exciting. And when I think about AI, broadly, what are the key components? I think of AI as two parts, the compute part and the data, right? So we collect data, curate it in order to train our model, and then the compute part is what turns the data into the model that we then actually use. And now if you think about the research we have done as a research community in NeurIPS and more broadly at similar conferences, overall I think it's fair to say that the focus for a long time has been on the compute side, right? There are literally thousands, if not tens of thousands of papers on questions around optimization procedures, model architectures, loss functions, and so on. And I think this is fantastic. We have learned a ton. We have really great architectures now, such as the transformer, and we are getting better and better at optimizing them. Of course, there's a second component, as I just said, and this is the training data. And I would say overall, this is still a much less studied field. And this is why we have a tutorial today specifically around data selection for training data for foundation models. And just a little bit of historic context why I think data is comparatively understudied still. If you think about how NeurIPS maybe looked like 10 years ago, 7 years ago, a lot of the research back then happened in the context of a specific training set, right? People would say work on ImageNet or MNIST or the Penn Tree Bank dataset, UCI adult, and then make progress with better modeling techniques within the scope of these datasets. And this is, as I said, this is great. We've learned a lot, and over time, for many, many, many different datasets, we've climbed up the performance ladder and made the models better and better. And yeah, we've learned a lot about modeling, but the catch is, since we have always kept the training sets constant in all of this, we actually haven't learned that much about how to build really good training data to begin with. And I'm not the only one who says this. Obviously, there's been growing awareness over the past few years that training data is really, really key. I think one paper that makes the case for this nicely is this: everyone wants to do the model work, not the data work. Data cascades in high-stakes AI. It's won a Best Paper Award at the Computer Human Interaction Conference 2021. And around the time 2021 is when a lot of efforts around data-centric AI started. For instance, Andrew Wang created the Data-Centric AI Hub. And then here at NeurIPS, one thing that I really, really like, I'm a big fan of, is the datasets and benchmark track, to have a dedicated venue here for work on datasets. And now if we go a couple of years into the future, I think everyone agrees, when you see new state-of-the-art foundation model releases like Llama 3, in the blog post describing Llama 3, they made this very clear that data curation has been a key component in the success of Llama 3, why Llama 3 is a really good model. And it's not just the Llama 3 crowd, also Qwen 2.5, if you look at the Qwen 2.5 Coda technical report, probably right now the best open weight model, and they also highlight data cleaning, data generation, balanced data mixing as keys to their success with their Qwen 2.5 models. Cool, okay, so training data, really important. How we curate good training data is really important, and this is what we're going to talk about today. We'll have 3 parts to this tutorial. Right now, we're in the first part, introduction, and I'll give you an overview of the state of the art in curating pre-training datasets for foundation models, both in the language domain and in the image text domain. And then in the next 2 parts of the tutorial, we'll take a step back and look at some more mathematically grounded principled methods. Okay, and then we have these short Q&A sections at the end in a break in between the different parts. And then we'll have a Q&A for all parts also at the end. Okay, cool. So let's get started. What's the empirical state of the art for data selection? As I just mentioned, we'll do this in 2 parts. First, language model pre-training data, and then multimodal image text training data. And just to underline again how important training data is, it's interesting to look at the GPT series of models and so just look at the papers, or the leaks around GPT-4, how much data these models were trained on. And sort of like over the 5-year period there, the amount of data these models are trained on has grown by more than a factor of 1,000. Similar story in multimodal learning as well. And at the same time, while these training sets have grown so much, there's actually a decreasing amount of detail on pre-training data, even for open weight model releases. So like, for instance, if you look at Llama 3 or Qwen 2.5 technical reports we just talked about, they release the weights of their models, but they don't release the training data. So I think as a result, overall, the research space around training data curation is still comparatively underdeveloped. And I think if we go back 1 year to 2023, there was a tweet that I found very funny because it sort of like summarized the state of the art at LLM training data in an amusing way. Sort of like LLM datasets be like, first you start with Common Crawl, then you add C4, which is just Common Crawl again, but don't worry about it. Eye of Newt and Toe of Frog. Then Wikipedia, also in Common Crawl, but again, don't worry. GitHub, permissively licensed, trust us. Rule of Bat and Tongue of Dog, books, just all the books, every archive paper, and so on. Basically, it was very, very ad hoc. And to be fair, at the beginning, sort of like as scaling is just giving you big gains quickly, just amassing more and more training data makes sense as a first step. But then after a while, it's also worth revisiting this and saying, okay, how do we actually build like a really performant training set? And over the past, let's say, 2 years, there's also been an increasing number of papers having a closer look at language model training data. For instance, this paper here from AI2, the pile, obviously, from Elutha AI, the Red Pajama datasets, and so on. In fact, more and more papers appeared, and this is great. I love that there's more research attention. But one tricky thing for me, at least, was when I looked at all of these papers, is that they all differed in their evaluation and training protocols. So basically, you had all of these different proposals for how to do data curation, but at the end, it actually wasn't clear what works best. Like, what is actually the best training set for training your next large language model? And in order to address this, collaborators and I, over the past, I guess now 1.5 years, put together this Datacom for Language Model project. Sort of like, this is a large group of authors, and don't have time, unfortunately, to go through everyone. I'll just highlight the key people at the beginning and the end of the author list. So Jeffrey and Alex are my PhD students at UW at Stanford. George is a PhD student with Alex DeMarcus at UT Austin. And Maor was a PhD student with Yair at Tel Aviv. And then sort of like the other sort of like leaders of the project together with me were Achal and Vaishal at the time at Toyota Research and Apple. Cool. And the goal here with this project was to basically build a framework for principled empirical comparisons of different data curation strategies. So like we can put everything sort of like into the same framework and see, okay, what really works best for building a state-of-the-art language modeling data set. And so overall, DCLM has 3 parts. The first one is the benchmark we put together for language model training curation. And then so you can think of this benchmark as our experimental platform. And once the experimental platform was in place, we did a lot of experiments to figure out what are the key pieces and how can we improve over the state of the art in pre-training data curation. And then the third part that came out of this project was a state-of-the-art public training set for 7 billion parameter language models. So this is sort of like the proof at the end that what we figured out is actually meaningful because we could substantially push forward the state-of-the-art. Okay, let's be a little bit more precise with what this DCLM benchmark actually is. So like as a participant, you're going through the following 4 steps. First, you select a scale that you want to participate in. Since language model pre-training can be computationally very demanding, we divided DCLM into different compute scales, 5 of them, so that we can compare approaches with the same amount of compute and then also look at scaling trends. Okay, so first you pick how much compute you have, what scale you want to participate in, and then now comes the key part, actually building a data set. There are 2 tracks to that. In the first track, you just use our data pool and build a subset from our data pool. In the second track, you can also bring your own data sources. If you have some training data that you think is not in Common Crawl, but is really, really good, feel free to add it in. And then once you have built your data set, you use the model training code we provided. We want to make sure everything is comparable, so everyone has to use the same model training code, and then we evaluate the model that comes out on about 50 downstream tasks. And then we can simply say, okay, the best training set is the training set that leads to the best model on our downstream evaluations. And so just to clarify here again, the key part for submissions in this DCLM framework is the middle one, where you figure out how to filter the candidate pool in the best possible way, or where you bring new training data that will make language model training better. So, and to be a bit more precise, again, what are these different scales? How does this look? So this table here has the 5 different scales, from a 400 million parameter model to a 7 billion parameter model. The -1x is the overtraining factor with respect to chinchilla optimal training. So 1x means that our training tokens follow the chinchilla scaling law. And then you can see this goes in terms of H100 training hours from about 26 for the cheapest scale to about 7,000 for the most expensive scale. And this is obviously a little scary, 7,000 hours for a single training run. But to be clear, we did most of our development of our training set at the smaller scale, specifically at the 1B, 1X scale. Okay, and then obviously one important question here is, okay, like if we have these different competition scales, does this actually matter? Like, is the best training set at the small scales, is the best data curation strategy at the small scales also the best data curation strategy at the larger scales? And we did experiments for this, and the answer is yes. So here on this plot, what you see on the x-axis, this does not work particularly well, so let's use this. What you see here on the x-axis is the performance on our evaluation suite for a given scale S. And we have 3 different scales here that we compare to the 7B scale. So the 7B scale is on the y-axis, and then blue means data curation strategy, you do it on the 400 million scale, and then we see, okay, how well does this correlate with the 7B scale? And we do the same also for orange, the 1B scale, and for the 3B scale, which is in green. And what you see overall is that there is some noise, but overall, the best training sets at the 7B scale are also the best training sets at the smaller scales. And this is really helpful for having a quick experimental loop, so you can try out new ideas at a small scale. If you see nice gains, then it makes sense scaling that up. If you don't see nice gains, let's go to the next idea. Okay, so this is the benchmark overall that we put in place with the different competition scales. Now the question is, okay, is this productive? Does this actually lead to better training sets? And the answer is very much yes. So one key outcome for this project was our state-of-the-art language model training set. And let's see, so let's parse this plot here together. On the x-axis, we have training flops, right? Everything in language modeling land gets better if you put in more compute, so we should normalize by the amount of compute we put in. So this is why we make a scaling plot with training compute on the x-axis. And then on the y-axis, we look at 2 different evaluations. One is sort of like an average over evaluation suite. Core is sort of like a core set of tasks that we picked because they have good scaling, so it's about 20 of them. And on the right-hand side, we have MMLU, which is a specific test set that many people pay attention to, so we broke that out into a separate plot. And then there are lots of points in this plot here corresponding to basically almost all the open weight models we could find and run, and then also know how large the training set is, and then we plotted all of this. And so like the nice thing here is that the orange line, which is our DCLM training set, is sort of like Pareto optimal here. For every amount of flops that we look at, DCLM, the training set, gives you the best language model. And then if you compare this, for instance, with the Llama 3 8 billion model, the red X here, that's about 6x, so 6 times more compute efficient. So you can go into the same performance region as the Llama 3 8B model by using only 6 times less compute, which is a big increase, right? So this was pretty exciting for us, and various people have then already built on top of this data set. Okay, cool. And I think this is also particularly nice because yes, like Gemma and Llama, it's great that they release their weights openly, but for both of these models, we don't know what the training set looks like. So here with DCLM, we have a pair of like a good 8B or 7B model and the corresponding training set publicly available. Okay, so in the next like 10 minutes, I want to go step by step through our pipeline for building this state-of-the-art training set. Okay, and so at a high level, there's 4 parts to this. The first one is you need a big data source. And basically, like for almost all efforts in language modeling, this is Common Crawl. And then, okay, good, you take Common Crawl, it's a web crawl, so you have a lot of HTML. So the next step is text extraction from the HTML to find the main text on a web page, which is trickier than you may think. The third part, which is probably the most important one, is the data filtering you do on top after the HTML extraction. And then the final step is deduplication. Okay, cool. Like starting point, Common Crawl. I'm sure many people have heard about Common Crawl. Just to recap, because this is, I think, a very, very important project. So it's a public, non-profit internet crawl, operates since 2007, and they've been doing roughly monthly web crawls and then release a large dump that they collected over the previous month. And in total, they have accumulated about 10 petabytes of data that is stored in an S3 bucket, freely available for everyone to download, and contains about 250 billion web pages. And basically, this is our candidate pool that we provide as part of DataComp for people to start for their data filtering experiments. So overall, if you do text extraction on top of that, you get about 240 trillion tokens. Okay, cool. And just to highlight again how important Common Crawl is, I think a nice comparison here is this XKCD comic. Sort of like at the top, you have all modern digital infrastructure. And sort of like, I think in our case here, this is the current AI revolution. And then there's this little pillar there. In the XKCD comic, it's a project some random person in Nebraska has been thanklessly maintaining since 2003. I think in our case, this is Common Crawl, because for the longest time, Common Crawl has really been two people, like one technical person, one person in charge of an organization, and they really created the foundation for a lot of progress in language modeling. So I think big thank you to Common Crawl. Okay, so now we have all of this data from Common Crawl, and basically what they're doing is downloading a lot of HTML, and you can't just train directly on the raw HTML. So the next thing you need to do is take those HTML sources and extract the main content of that website, where you get rid of all of the markup, all of the menus on the sites, all of the ads and so on, and only have the relevant text. And this is surprisingly tricky. I don't think this is well studied. I think there's definitely room for improvement here. Just to give you a sense of, can you actually make progress here? Wet files, the bottom row in the table here, this is what Common Crawl distributes as text extractions. And then the other two rows in the table here are two libraries that we tried out in order to see how much better than the wet files can we get with better text extraction from HTML. And then you see quite significant gains on our core metric. So this is on the 1 billion 1x scale. And usually in that regime, in a smaller model regime, the core metric is what we look at most. Okay, so this was nice. We got some gains here from HTML extraction. But as I mentioned, the key part really is data filtering. And what we did for data filtering, sort of at a high level, you can divide it into two steps. One is heuristic filters. Specifically, we'll use the heuristic filters from Refined Web, which is an existing open effort for building a good pre-training data set. And then the second part is a train classifier. Let's be a little bit more specific. What do I mean by heuristic filters? So these are manually designed rules in order to remove some of the training data where a researcher decided, this looks like low quality data, let's remove data like that from the training corpus. And some examples for these heuristic filters are language-based filters, page length, then in-document repetition, filler words, they have a specific URL band list, and so on. So this is all important to like get rid of some of the data. And then the second part that we used is a model-based classifier. So the idea is, okay, this hand design of filters is nice, but probably it's quite hard to design really good filters that work comprehensively for all sorts of websites. So natural machine learning approaches, let's just try a model to classify or to score documents and decide if they are high quality or low quality, if we want to include them or not. And this is exactly what we did. Now the tricky thing is now the question becomes, what is good training data for your data filter, right? So like we are sort of like have the same problem now one level higher up, right? We want a classifier that tells us what data to train on. Now we need the training data for the filtering classifier. And the intuition is you have positive examples that are high quality documents. which is obviously subjective, but at least something you can experiment with. And then negative examples is sort of like maybe an average document from the candidate pool you want to filter. Okay, and let's look at a couple different approaches here. So this is again at the 1 billion parameter scale. Refined web reproduction, this is just what the refined web. We had to reproduce refined web because at the time this wasn't fully published. So if you just train a model on refined web, you get 27.5 on core. And then here's basically a long list of approaches that we tried as baselines for us to figure out what works best. Like the Common Core comes with PageRank score, so you can use PageRank in order to score your websites. But this is actually doing worse than just doing no filtering, right? So the 27.5 is the no filtering baseline here. And some things like perplexity filtering get noticeably above the no filtering baseline here. The best thing we found was fast text, which is a bigram classifier combined with a very specific training set for the filtering model. So this is what I'm going to talk about next, because this was really key here. So now these results are the larger scale, 7 billion. And what you can look at now here is, this is the filtering threshold. So we look at the top 10% of examples where we use different data sets as positive examples. Okay, so the negative examples for the filtering model always stay the same, just random samples out of our corpus. And then the positive examples are a Wikipedia, a reproduction of Open Web Text 2, then an approximation of what they did for the GPT-3 paper. And then what we sort of like found to work very well is Open Hermes 2.5 plus the explain like I'm 5 subreddit. So don't ask me exactly why these two, but they work surprisingly well. Just for context, Open Hermes 2.5, this is a good instruction tuning data set. Normally this is used for post-training, so like for fine-tuning a language model. We found that these are also really good examples to filter your pre-training data. And then the idea with the explain like I'm a 5 subreddit was that they have simple explanations, and this is sort of like something we want to also find in our pre-training data. And the important thing here is sort of like as a baseline, we can again look at no filtering. At the 7 billion model parameter scale, if you just do refined web or reproduction, you get 38.3 on core. So all of these other data sets here as positive examples actually do worse than doing no filtering. So this was quite surprising to me because like we think of Wikipedia usually as high quality data. It's like comprehensive, like well curated by humans, sort of like by humans as an encyclopedia. But it turns out if you use Wikipedia as positive examples in your data filter, this is actually substantially worse than using Open Hermes or other instruction tuning data sets. In fact, using Wikipedia for your data filtering is worse than doing no data filtering at all. And I think overall, this is quite unclear to me still. I mean, obviously we made the numbers go up, so we found something that works, but sort of like the principles behind this, I think, are still an open research problem. And one thing that we also found interesting was that humans are not necessarily good judges of data quality, right? So sometimes we think of like, okay, data quality is something that a human could assess, but it's important to keep in mind, humans don't really understand how language model training works either. So in the end, what we care about is the data good from the perspective of language model training, not is the data good from the perspective of a human reading it. And sort of like these experiments we did here are of the following form. We had 500 documents from our corpus, and then some of the experts on our paper who worked with this data a lot, they annotated these 500 documents as good or bad data. Like, did they think this is good or bad training data? And then we looked if the human quality judgments correspond to the performance of the models you get from training on the respective data. And sort of like this is what these plots here are. Here's the ROC AUC, area under the curve, on the maturity labels. And the y-axis is the performance you get for training a model. So what does this mean? So the blue point here, which is the Ask LLM approach for data filtering, that one has the largest agreement with our human annotations, but it leads to the worst model when you actually train on it. While these orange axes here, these are variations of our fast text classifier, they have little agreement with our human maturity labels, but they lead to the best language models. Yeah, as I said, I think this is still, I think, early days for data curation research. Understanding this better, I think, would be great. Okay, deduplication. In the interest of time, I'm just going to say we did a lot of experiments. Deduplication is important. It makes the numbers go up. I think the exact details of that are also still to be figured out. So there's already some interesting follow-up work where people pointed out that you can do deduplication in a better way than what we did in DCLM. And then just to sort of like put it all together at a high level, what is sort of like the flow of documents through our data curation pipeline? At the left, we have the DCLM pool, as I mentioned, 240 trillion tokens. And then the first stage here are the refined web heuristic filters. So all of these are basically manually human-designed filters. There's duplication. And then the last stage is the model-based filtering. So overall, only 1% of documents actually make it through this pipeline. And I think this is another sort of way to look at this and to see that, okay, there's probably, hopefully, still room for improvement here, because overall these pipelines at the moment are very aggressive, right? So like we only keep 1% of the data that we got from Common Crawl for the actual training data set. And this is okay because there's just a ton of data in Common Crawl. But as we now make our language models larger and larger, one concern people increasingly have is that we may run out of data. And if we run out of data, well, if we only at the moment keep 1% of the data in our pipelines, hopefully there's some room for improvement here to increase the recall while keeping the quality level high. Cool. We only have a couple more minutes for the first part. So I'm going to skip about something around data mixing and just briefly mention that there's been a lot of interesting follow-up work. So like DCLM came out in June of this year. And over the past couple of months, there have been more awesome public LLM pre-training dataset releases. And I think the last one that just came out, I think 7 days ago, yeah, exactly a week ago, Nemotron CC from NVIDIA, they make nice progress on top of DCLM. So as I mentioned, overall, well, the name of our dataset, DCLM baseline, already suggests we just view this as a starting point. And I think there's a lot of room for improvement on top. Okay, now the multimodal part. Again, in the interest of time, we'll go through this a little bit quicker. Probably many of you have heard about the Lion 5B dataset. This is actually won a best paper award here at NeurIPS in the datasets track now 2 years ago. And this was great because this enabled a lot of research in the public on multimodal learning. Like Stable Diffusion, for instance, was trained on Lion. And this looked great on small-scale experiments. So like if you train a small clip model, then we could match the performance of the OpenAI clip models. But the catch here was that as we increased the model size and trained larger clip models, we had an increasing gap to the performance numbers that the OpenAI clip model achieved. And then we were like, okay, probably our training code is good enough. From some other experiments, we knew that. The cause for the discrepancy is probably the training data. And then the question was, okay, how can we improve over the Lion 5B dataset? And this is what motivated us to start the first Datacom project. So this is now in the reverse chronological order. Datacom for language models, this is what we did sort of like up to the summer. But sort of like 2 years ago, we started this Datacom project in the context of multimodal learning in order to build a state-of-the-art multimodal pre-training dataset. And it's the same idea as what we just talked about in DCLM, that we want to build a benchmark for data curation. And here in the context of image text data. Again, it has multiple scales so that people can compete at different pre-training scales. And just quickly skipping forward to the results here, the cool outcome was that if you train a clip model with the same amount of compute now as we had in the first 2 rows here, with the Datacom training set, you can actually outperform the OpenAI clip model. So same amount of compute, but now you get higher ImageNet accuracy than what the Lion trained clip model achieved and what the OpenAI trained clip model achieved. Okay, there's a lot more to talk about, so like how we tuned this data set. I'll skip forward again. These are all the submissions that people have made last year to the Datacom leaderboard. One thing that I found very interesting, and sort of like tying this back to the first part, is that the top entries here on this leaderboard, again, made progress by improved model-based filtering. So I think overall, this is more evidence that for these data selection, at least on the empirical side, for these foundation model data selection sort of like pipelines, one really key way to improve them is better model-based filtering. This led to state-of-the-art data sets for multimodal learning and for text-only learning. Again, there are a lot more papers. This is the 2 papers that went into the state-of-the-art thing on the leaderboard. But in interest of time here, I have 15 seconds left for my part, so I'm going to conclude now. Okay, I motivated this at the beginning. Training data is key for foundation models, both in the language and in the vision domain. And we have seen large improvements from better training data curation. So like sometimes a factor 6, in the case of Lion, a factor 9 times more compute efficient. And I think overall, these data curation benchmarks have been really key for highlighting what really works best empirically. We've done this on the model improvement side for many, many years. These benchmarks like CIFAR10, ImageNet have been key for highlighting what works best on the modeling side. I think it's important to do something similar also on the data curation side. As I just mentioned, model-based filtering has been the most important part in both domains, in language and in vision, in order to make the training sets better. And the current methods are still very much ad hoc. I think I mentioned this a couple of times throughout the talk, sort of like, I can't tell you necessarily the key principles behind what works best at the moment. I can't tell you how much room there's still for improvement. Empirically, there's still a lot of room for improvement. And I think understanding this more from an empirical and theoretical perspective would be really awesome. So for now, I leave you with our URL, datacomp.ai, so you can look up the datacomp work. And for DCLM, we also have a poster in the Friday afternoon poster session. Cool. Thanks a lot, and we have time for a couple of quick questions now.
Hi, this is Somit Gupta. I was wondering if you have any thoughts on post-training data curation and selection and similar efforts.
Yeah, that's a really great question. So this is actually exactly what my group is working on right now. So you can apply the same ideas of like doing a data-centric competition also for post-training data. We've been working on that now for a few months, and it's not public yet. We have some internal results. We're still building some infrastructure. So happy to chat about it later if you're interested.
Hi, I'm Arif Jafari, and I have a question about the way that you collected the data for the pre-training. What you do for balancing the data for some different tasks for the pre-training data. Let's say for code generation or mathematical reasoning, these sort of things. Do you think is that important to make the data balanced, or no, we don't need for pre-training?
Yeah, no, this is a great question. Just to recap quickly, sort of like, what about balancing sort of like code data, math data, and so on? Overall, the focus on DCLM has been mostly on sort of like natural language understanding type benchmarks, less on code. You can fold in some code data, but we felt there was already a good amount of research effort around better code data sets. And we could just add this in. Sort of like how to do this mixing exactly, I think is a great question. I don't sort of like know the perfect answer there. I've seen some interesting research that depending on which phase you are in training, you may want to train on more code data depending on where you are in training. But I think that's still all sort of like TBD.
Okay, thank you.
Thank you.
Oh. Yeah, thank you so much. Very nice talk. And I have a question about the synthetic data. So do you think this pipeline, this data pipeline would help us to build the synthetic data?
Great question. So I think synthetic data is very important. This has not been immediately the focus of Datacomp because we wanted to start with sort of like data selection and making sure we can curate the existing data in the best possible way. But this is sort of like, from our perspective, the idea was, okay, we'll have this track on bring your own data. This is what we usually call it. Here, the bottom part, the mixing track, where if you have really awesome synthetic data, please still submit it to the leaderboard, and it would be great to see how much it improves compared to the data we have from Common Crawl.
Okay, thank you so much.
Could you go back to the state of the 2023, early 2023 training?
You mean the tweet?
No, the list of, and go,
This?
okay, hold on, that one? And go one back? Sorry, and then go one forward.
I'll post the slides.
No, can you go one more?
I'll post the slides, okay?
Can you go one more, please?
One more? Okay. We have to keep track of.
Okay. Thank you. Can you talk a little bit about if you have faulty data on the internet, how do you, if Common Crawl is using grabs of data from a moment in time, how do you make sure that the corpus of data, to the extent, let's say press publishes articles that says, I don't know, the sky is, whatever it might be, like, and you use a moment in time set of data, and subsequent information makes us realize that data was incorrect. How do you, if a model is trained based on that moment in time, how do you make sure that we're using the correct data, not only just correct, that's probably the wrong terminology, that we're using data that's accurate?
Yeah, good question. And I think overall this is a research problem. I can tell you right now, I guess, how this maybe happens to some extent in the DCLM pipeline is we have the fast text classifier that is trained with examples of high quality data and low quality data. So hopefully on average, the classifier will select the data sources that are more correct. And then overall in the pre-trained corpus, I think it's fair to say that things don't have to be perfect. I think if there are some examples that are a little bit wrong, as long as the majority of the documents on a topic are correct, the model will probably pick up the correct documents and learn that as sort of like true knowledge.
Thank you.
But there's always more to do there. Thanks a lot. Maybe one last question, and then you can already come and set up.
Hi, thanks so much for the talk. You mentioned that as data dries up, recall could be key. I'm curious if you thought any of that 99% of Common Crawl you don't use, if there's any low-hanging fruit in there, particularly things that maybe heuristics prune out?
Yeah, great question. And I think for that, I would just refer you to the Nemotron CC paper here that I quickly mentioned, because I think they specifically made progress by changing the order of how you do the filtering and doing less heuristic filtering, more model-based filtering. Just thinking out loud, I think this model-based filtering probably you can also do in a better way, just from having looked at some of the data. But yeah, I mean, it's research. I can't tell you anything definite, sorry. Thank you. Excellent. Cool. Thanks again. And
just one more question.
Okay, go for it.
Yeah. Having large amount of low quality data versus a very small amount of high quality data, which is more likely to yield better results?
I mean, I think it depends. It depends a lot on the context, right? If you have a small amount of high quality data, you can't train a large language model on it, at least with current techniques, right? So let's say you had like 100 million tokens of very high quality data. Like the 7B models are trained on trillions of tokens. So I think that's not going to work. You could repeat the data a ton, but it often shows diminishing returns quickly. I think, at least what we have seen here a bit, and in the context of the multimodal data compass, if you have really high quality data, that could be good training data for your filtering model. The idea being that you can boost sort of like what is good data via the filtering model to the entire corpus, and sort of like use this as a signal for what is very good data. But I think at the moment for pre-training, volume is just very important. So, I'm happy to talk offline also. Let's go to the next part. Thank you.
All right. In the interest of time, I will just get started right away. My name is Ruoxi. I'm an assistant professor at Virginia Tech. So thanks, Ludwig, for the deep dive into the principled experimentation for data selection. If you think of data selection as a game, the first part is more about defining the rules of the game. And this part is really about how we can win the game with some well-founded techniques. So this is a roadmap for this talk. We'll start by talking about some first principle objective for data selection, which is directly optimizing the model performance. And we'll talk about Some key challenges as we implement this objective. We will have potentially a large search space, and the objective function itself might be very complex. Then we'll break down the problems into two categories. We'll first focus on some problems where the search space is manageable. So the first challenge is not blocking our way. But we still need to address the second challenge, and then I'll introduce some big ideas for handling the complexity in the objective itself. We will see how the combination of this objective complexity handling techniques in combination with a manageable search space eventually lead to some practical algorithms. And then we'll talk about some general problems with really large search space. And in those cases, we must rely on some secondary principles or heuristics. Although those heuristics may not perfectly align with the true objective that we want to optimize, they often yield some strong results empirically. So that's a roadmap. Let's start with the first principle objective data selection, as well as some challenges. Before we dive in, let's just broadly talk about what data selection means in this tutorial, making sure that we are all speaking the same language. So depending on which units you are trying to select, you can broadly categorize data selection into selecting data source, or point, or the token. So data source may be an entire data set like Wikipedia or Common Crawl. And in the middle scale, we have data point. Data point is just a unit in your training batch. In language modeling, it would be a chunk that contains a sequence of tokens. And in image modeling, it will be some single image in your training batch. And in the finest green level, we'll have token selection, which is the smallest unit processed by the model. Intuitively, as we move from the kind of general level of source selection all the way down to the token selection, we'll potentially kind of envision more performance gain per token. But at the same time, because we are spending more time to do the selection, we'll encounter maybe higher computational overhead. And there are some other axes that we can categorize data selection. We have hard versus soft selection. Hard selection just means that all or nothing, it's a binary selection. And the soft selection is more nuanced. It assigns some continuous weight to each selection unit. And there's also this offline selection versus online selection. Offline just means that we make all the data selection decisions before the actual training run. And online data selection means that we are trying to adapt our data selection decision during the training process according to the current state of the model. All right, with that in mind, let's take a step back and look at what we would like to ideally achieve for data selection. The first principle view of data selection. Ideally, we view data selection as an optimization problem. Our goal is to identify some subset that best improves a given objective US. So the subset here is denoted by S. And this objective could be improving the generalization of the model, or improving specific testing performance in fine-tuning, or even more generally, safety and fairness. And practically, we may also have some constraints. For example, we may have to work with some limited computational limits, as well as acquisition budgets. Okay, so that's direct optimization. We are trying to directly selecting a subset that can maximize the objective, which is usually model performance. That will be the focus of this talk. But there are some challenges, daunting challenges for doing this. The first challenge is computational complexity. The search space could be very large. For example, imagining selecting some data points from millions of billions of data points. And secondly, this objective itself may not be closely kind of well-defined. It may not have a closed form formula so that we can easily optimize. So this objective itself might not be straightforward to optimize. Okay, so to make some progress, we have to first narrow down the search space. We'll first focus on some scenarios where the direct optimization becomes more feasible because the search space is relatively small. And there are two specific problem instances. One is source level optimization, meaning that instead of selecting individual data points or individual token, we are trying to operate at the source level. And the other problem instance is online batch selection. So instead of selecting from the entire data corpus, we are trying to focus our selection decision for the current batch. We are trying to select some sample from the current batch and make the selection decisions incrementally. So here is where we are in this roadmap. We talk about the first principle objective, some key challenges. And next, we will focus on the specific problem instances with manageable search space and see how we can additionally address the issue of complexity in the objective. And I will talk about some big ideas and see how these ideas eventually lead us to some practical algorithms with well-founded principles. Okay, let's dive right in. Data source selection. So in this talk, I'm gonna use source and domain interchangeably. Data source selection is usually solved in this context, meaning that we almost never completely discard a data corpus because that means losing a lot of valuable information inside. So usually we'll just reweight the domain represented by each data corpus. And the common practice in this space is just trial and error. We just try a bunch of weights and see which works better. And there's some early work in the space that is essentially driven by some intuition. And the intuition is that if we upweight the difficult domains, we'll help the model learn better and faster. And this process usually involves first define what difficulty means and then transform the difficulty score to some appropriate weighting scheme. But the challenge here is that it doesn't guarantee that reweighting will improve the downstream performance because there is a gap between difficulty and model performance. And usually there is considerable room to improve in terms of effectiveness. So recently, you can see the shift that is happening in the literature and try to move towards the direct optimization, where the goal is to try to find the optimal domain weights that directly maximize the metric of interest. In this case, it's usually validation loss. So previously I have talked about this objective where we try to select the data sets that maximize the utility function. But here, because we are focusing on the reweighting, I'll just rewrite it explicitly highlighting that the optimization variable is P, which is a weighting vector, and it lies on a simplex. All right. So in this case, UP, our utility function, is instantiated to be the negative validation loss. That ensures that when we maximize the negative validation loss, we are trying to actually minimize the validation loss. Okay, so let's write it out more explicitly. So here L is loss, and D subscript val just means validation data. And this theta star of P represents the model that is trained on a data set that is reweighted according to the weight vector P. So this theta of P itself is a model trained on a data set, meaning that itself encodes the optimization process. So overall, it will actually lead us to a bi-level optimization, where theta of P is defined by another optimization objective that represents training on a weighted data set. So in particular, this D of I represents the training data from domain I, and the PI again is a weight for that domain. So this inner optimization represents that you train on the weighted data set. All right. So bi-level optimization, the formulation is very clean, but solving it is very challenging. Although it is a long-standing problem in optimization literature, but usually, if you apply some traditional techniques, you have to rely on some second-order derivatives. That is because if we want to optimize P, we have to differentiate through the training process and check how much the training loss changes when we change the P a little bit. So that is very challenging. The big idea now in the space is so-called surrogate modeling. In a nutshell, surrogate modeling is trying to approximate this super complex function that we are trying to optimize with some easier to optimize surrogate. In particular, we are going to fit a parametric function, which I will call it mixing law, that maps the mixing ratio or the weight P to the validation loss. So we're going to replace or approximate this complex objective here with some simple parametric function, u subscript p, u subscript w of p, and w represents the parameters of this parametric function. And the beauty is that once we have a good approximation for this objective, then we can find the optimal width by directly optimizing the surrogate. And because this function is parametric, it might be simple, and optimizing it is very easy. We can just use some gradient techniques, for example. Okay, so now the big question is that how can we estimate the mixing law? How can we estimate this parametric function that approximates the validation loss? Well, the idea is very simple. We are in the NeurIPS. We know how to estimate some function. We collect some data, and then we fit some function according to this square, for example. Specifically, we can first sample some different mixing ratios, p subscript I, and then we'll train a model for each mixing ratio and calculate the corresponding validation loss. Right? And the third step, we're going to call this P paired up with a validation loss, the mixing law training data, because we're going to use this data set to fit our mixing law. So gather this training data set, and then we'll fit the model U subscript W, and W, remember, is our parameter, using some very simple techniques like least squares. Okay, but there is one caveat. The second step here is very expensive because for each data point that you collect in the second step, you need to retrain the model. You need to retrain the model on a new mixing ratio and calculate the validation loss, and that is very expensive. So how can we handle the retraining cost? And how large is the retraining cost? Let's do some analysis. Let's think about the simplest model that we can imagine, maybe a linear model. So UW is a linear model. And in this case, how many parameters are there in the model? Well, that depends on W, and W has the same dimension as P, and P's dimension is the number of domains. So this means that in the simplest form, we'll have the number of domains, this number of parameters that we need to fit. And to fit this number of parameters, we'll need to at least collect this number of data points. So basically, it means that if we have M domains, we'll need at least M retraining runs to collect the data and then find the mixing law. So this is still very expensive. But if you think about applying the similar idea to the level of data selection where we need to retrain the model on the scale of the number of data points, this is much more manageable. That's why I call it manageable search space. All right, so how can we manage the retraining cost? The first step is to choose the right functional form. The general intuition is that the simpler the function form is, the less data it requires for us to fit accurately. For example, there are some existing functions that people have explored in the literature, like linear exponential power function. But the reality is that even retraining at the scale of all domains can still be very expensive. So we need some additional ideas. So there are two ideas to help us cut the cost further, with the central theme of kind of cutting the cost for each retraining run. One idea is instead of training the large full-scale model, you train a proxy model. And then approximate the validation loss using the results of a proxy model and then fixing the missing law using the proxy model's results. Another idea is to, instead of training on all the data, we retrain only on a small scale of data. But there are some caveats. For proxy models, there is a concern about how closely a proxy model can mirror the behavior of the original model. So usually, it may not kind of closely follow what the target model behaves. For example, in the figure on the left, so what you can see here is an extrapolation of validation loss with proxy model of different scales. And you can see that different proxy model give you different results. And the blue dots shows a ground truth validation loss. And proxy model may not tell you exactly what happens for the ground truth. So one potential solution is that how about we just retrain the true model that we want to predict its behavior, but at a much smaller data scale. That can also help us save the cost for the retraining. But there is a new challenge that emerged. The The challenge is that the optimal mixing that you found at a smaller scale may not transfer to the scale to a larger scale. So concretely, if you look at the figure on the left, which shows you the optimal mixing that is found for different scales. Different color represent different data scale, all the way from 30 million tokens to 1.3 billion tokens. And each column represents different domains, and the length, the height of the bar, represents the weight, optimal weight that we found for that domain. And if you just compare across different colors, you can find that the optimal weights for different data scale is dramatically different. And on the other hand, if you apply the optimal mixing that you found based on small-scale experiments, it may not work as well for some larger experiments. So the key message here is that the optimal mixing is really scale-dependent. We have to have a way to predict how optimal mixing changes as the scale grows. Okay, so here is the result that emerged from the recent literature. It tells us how exactly the optimal data composition will change according to different data scales. It is quite a long theorem. Let's break it down. So at the beginning, we consider an optimization problem. This is a kind of a rewriting of optimization problem that is trying to find the mixing ratio. Instead of trying to maximize, kind of optimize the ratio, we try to optimize allocation, the data points allocation for each domain, which is essentially the same thing. Okay, and we are subject to a constraint that the allocation for each domain sum up to the total constraint, the total data that we are budgeted for. Okay, so if we look at the objective here, it assumes the validation loss has this particular function form. And some term might be familiar to you, like you see some kind of power law scaling. And importantly, each segment here represents a powerful power law scaling for a different domain. So essentially, this assumes that the validation, the contribution of different domains are independent of each other. So you can fit a power law scaling to predict the loss of each domain and sum up together to predict the loss of the overall validation loss. This is a very strong assumption because usually there's some interaction between the domains. For example, if you add one domain, maybe it also helps reducing the loss on the other domain. So this kind of interaction is not captured by this kind of specific assumption for the validation loss. But in the paper, it also shows that even if the domains are dependent, as long as it can be decomposed into some independent scales, the same results that I'm going to talk about will still hold. Okay, so for simplicity, let's just stick with the current assumption, where we have validation loss that can be predicted by this specific form of independent scaling law, the sum of independent scaling law. All right, so next I'm going to define a notation, which is called C star of n. Remember, n is our total budget. C star of n represents the optimal allocation for each domain for that budget. Okay, so it will be a length m vector if you have m domains. Let's suppose that now we have two budgets that we already know what is optimal allocation. And I'll call it C star of n1, C star of n2. And this theorem says that you can define a new budget in this way, and its optimal allocation can be completely determined by the optimal allocation for this existing two budgets that you already know the solutions. This is a very powerful result because it tells you how to predict the optimal allocation for a much larger scale based on some small scale results that we can already obtain. Okay. So let's see how well this kind of predicted allocation or predicted weights actually work empirically. So here, the auto scale, the red line, represents the validation loss if you train on the weights predicted according to the scaling law in the previous slides, as well as the direct optimization framework that I have covered. All right, so the baselines are some existing work as well as the weights that you trim llama models, as well as some uniform weights. And you can see that in comparison with llama weights, this new idea can achieve 28% faster in terms of loss reduction, and compared with uniform, there is even more improvement. It not only improves the validation loss, but also the downstream performance, which is shown in the red figure, where it is evaluated over different tasks in MMU, and this new weight also improves the performance, the task performance. All right. So keep in mind that we have just wrapped up a specific problem instance with relatively manageable search space. And we have shown that how to form a principled yet effective solution if we have a specific, a manageable search space. Now I'm going to move to another example of a problem that has manageable search space, which is online batch selection. The setup here is that at each training iteration, we have a batch of training data candidates. And the goal of online batch optimization is to choose samples within the batch in order to improve the performance as much as possible. Mathematically, we are going to optimize this subset within the current batch, which is denoted by B subscript T. And in the objective, we are trying to maximize the loss improvement. Specifically, theta T represents the current model, and theta T plus 1 of S represents the model if you update your model with the select data S. All right, so if we do gradient descent, this theta T plus 1 of S can be written out explicitly. It is just theta T updated with the aggregate gradients over S. Right? So while this seems kind of much tractable compared with data point selection, because right now our candidate is just small batch, but direct optimization still is non-trivial in that it has discrete search space. If we just naively optimize this objective, we have to exhaustively search over all possible possible subsets and try to see what is improvement achieved by each subset and find the best one. We have to have some idea that can overcome this combinatorial effect. Okay, so the key insight here is that this objective in online batch optimization is looking at improvement of loss. And usually, the improvement of loss is very small. So that lends itself to some local approximation. So the big idea is that because it's small, so local approximation might be accurately reflect what the true objective looks like. So specifically, you can use first-order Taylor expansion around the current model theta T. And if you apply Taylor expansion, you will get the gradient of the loss at the validation data multiplied with the change of the model. Because the model change is driven by gradient descent, you can plug in the gradient descent step inside, and overall, with local approximation, you can arrive at the final line, which says that this loss improvement can be approximated by the gradient of the validation dot product with the gradient of each candidate within your set, and you take a sum over all the data points in your set. All right, so how faithful is this local approximation? It's not bad. This is an experiment done in this paper. So on the y-axis is the true utility. Remember, in our context, the true utility is this improvement of loss. And you can see that when the true utility is very small, the predicted utility based on local approximation is fairly accurate. But if the true utility is large, then this prediction is kind of more off. This also is expected because the local approximation is expected to work if you have small perturbations. All right, so let's wrap up this objective here. Remember now with local approximation, we have arrived at a objective, which is just a sum of gradients of the sum of the dot product between the validation gradient and each training gradient within the set. Okay, so if you look at this function, you'll find that it is additive function over this chosen set S. The contribution, this essentially says that the contribution of each data point Z within S is independent. Okay, you just take the product, dot product of the training gradient with the validation gradient and then sum them all up. So what is the optimal solution? If you stare at it long enough, you'll find that the optimal solution is very simple. It is just basically you calculate the gradient dot product for all data points and pick the top performers. So that essentially simplifies to the top case selection. And your scoring rule is based on this dot product. You calculate the dot product with a validation gradient, and then pick the data points that has highest dot product. Okay, so that greatly simplifies the problem. But there is still practical challenge. We'll try to implement it in a foundation model scale. What is the challenge? So recall this is our scoring rule. Z is our training data. And we score this training data based on its gradient dot product with validation gradient. We have to compute this score for each data point in the batch and pick the best one. So if you look at this, we have to have the access to the gradient at each individual training point, which we call per sample gradient. How can we get per sample gradient? Well, it's not an easy task. So we know that deep learning frameworks is usually optimized for batch processing. So if you want to get like per sample gradient in a naive way, it means that you have to kind of backward pass your model with a batch size of 1, which is very time inefficient. And that's not the only challenge. So if you want to calculate this dot product, we have to instantiate the gradients in our memory. Imagine now you have some foundation models and you have a large batch. This is just not possible. You can't fit all the gradients in your memory. So that is a memory challenge. How can we tackle these challenges? Here are the ideas. The big idea is that we are going to use some intermediate results that we can obtain during backpropagation to recover these quantities that we are interested in. All right, so let's first look at how we can calculate per sample gradient without the need of one-by-one backpropagation to save more time. Okay, so this is, I will use the example of linear layer, but this idea is completely extensible for some more general types of layers. Okay, so on the left is the quantities that we are interested. We are interested in calculating the gradient of individual loss at a specific data point with respect to the model parameters. If we break it down, it is equal to the outer product of individual pre-activation with individual loss, the gradient of the loss with respect to the output of the linear layer. So just I want to highlight here the loss is defined over that specific sample. But the challenge is that in backpropagation, we actually only have the gradient, the aggregate gradient over the entire batch. So how can we calculate this quantity with aggregate gradient over the batch? So the very interesting fact that you can notice here is that here in this derivative, we are trying to look at the derivative with respect to the output. And because this output does not depend on the other data points in the batch, so this per individual gradient is actually equal to the aggregate gradient with respect to this specific output. So that's a fact that we can utilize to actually recover the per sample gradient just based on the aggregate loss gradient with respect to the output. And finally, we arrive at these two quantities and we take outer product, and both of these quantities are already available during the backpropagation. Okay. So we still haven't talked about how we can make a more memory efficient process to calculate the dot product. Okay. So remember, the challenge is that we can't really instantiate two gradients at the same time in our memory. So we have to kind of calculate in some more memory efficient way. So here is a dot product of the two gradients that we want to calculate. That is our score that we're going to use to rate the importance of the data. And each of these gradients can be calculated by the outer product between the pre-activation and the output gradient. And we can apply the same process for the other gradient. Okay. And there is a known identity that the inner product of two outer products is actually equal to the product of two inner products. Okay, so with this identity, you can eventually reach to this final line, which says that when you want to calculate the gradient dot product, you don't actually have to instantiate the gradient. You just need to take the inner product between the pre-activations, inner product of the output gradients, and then multiply the two scalars together. And keep in mind that these pre-activations and output gradient have much smaller size than the actual parameter gradient. So this is much more memory efficient than directly calculating the dot product between the gradients. Okay, so I want to highlight that the two techniques I just talked about can be applied much more generally. So many data selection methods, especially those that emerged before foundation models, heavily rely on gradients. And if you use this idea of leveraging intermediate computations, it can actually be applied to this existing data selection-based data selection methods and making them more practical at a foundation model scale. And here are some examples that can be actually improved by these ideas. All right, so now let's look at how it works out if we put everything together. We have this local approximation, and then we talk about some efficient techniques to calculate the dot product. How well it selects the data. So first, let's look at the overhead. So to quantify overhead, we compare with the throughput of the regular training. And you can see that this kind of grid here refers to the method that put everything together. You can see that the throughput is in comparison with regular training. And here, grids direct means that you use kind of dot product to select a data, but you just calculate the dot product naively. And you can see that it's dramatically reduced the throughput. This result really highlights that in data selection for foundation models, it is super important to be mindful of your implementation. If you don't implement it in an efficient way, it doesn't help in terms of efficiency. Okay, so, and the following are some results for data selection for fine-tuning with only 5 validation points from each task. And you can see that it can increase the divergence rate, convergence rate, as well as leading to better downstream performance. Okay, so now let's look at this roadmap again, look at where we have come. So we start with first principle, we talk about key challenges, we specifically look at those problem instances with a kind of relatively small search space, so that the first stage is not in our way. And then we talk about 2 big ideas, surrogate modeling and local approximation, for us to simplify the objective, and that eventually lead to some practical algorithms that not only empirically effective, but theoretically founded. All right. But more generally, we have to acknowledge that direct optimization for some really large decision space is still very hard. What are some examples with very large search space? Well, you can think about data point selection directly from the entire data set, not from the batch. You can also think about even the token selection. And there is another layer of complexity for these general problems. If your selection units are too fine-grained, there might be some very complex interactions between each selection unit, between point to point, token to token, that cannot be captured by some simple approximations. So because it's so challenging to apply first principle objective for this large space, practitioners usually turn to some secondary or heuristic principles. Here are some heuristics, difficulty, diversity, counterfactual, which I will dive in just in a moment. Okay, but the bottom line here is that these heuristics do not guarantee alignment with original objective, but they are far more computationally manageable in practice, and they usually deliver some strong results in practice. Okay. So this is the roadmap. Now we are going to move beyond and look at some general problem instances with super large search space. And we're going to talk about some secondary principles that can eventually lead us to practical algorithms. All right. Okay, so first heuristic, difficulty. The core idea is to prioritize samples that model finds challenging. This is closely aligned with some traditional literature on uncertainty sampling of active learning. So the belief is that if we train on some samples that the model is struggling with, the model can learn better and faster. Some examples, you can characterize difficulty based on like how many times a correctly classified sample becomes unclassified. And you can look at the norm of the gradient. The larger norm, maybe it's more difficult. And you can also, well, there are some other interesting ideas that kind of have more nuanced characterization of difficulty. So the idea here is that if the point is difficult throughout the training process, maybe we shouldn't learn it anyway because it doesn't bring us any benefit. We should maybe look at those samples that are difficult at the beginning, but it can eventually learn. Okay, so you can characterize somehow it's kind of addressable difficulty. We are looking at those difficult samples that can be eventually overcome. So this can be characterized by the loss gap. You can look at the loss of under the current model, which tells you how difficult the sample is for the current model, and then you can rely on some external reference model, which is denoted by the theta ref, to characterize how difficult this sample is inherently. All right, and this loss has been, this idea has been utilized by token level selection. But the core challenge for difficulty-based selection is that there is ambiguity in difficulty. Both high-quality rare data and low-quality useless data can both appear to be difficult for your model. And another level of challenge is that you don't have diversity. If you have similar samples, they often kind of receive similar difficulty scores, and therefore this will lead us to like kind of get a cluster of similar samples, either all selected or all discarded, and which reduce the diversity of the selected set. Unfortunately, this is a challenge not specific to difficulty-based selection, but all scoring-based selection methods. If you just use one score to characterize the data's informativeness, then you will always end up at this situation. You either select some data together, similar point together, or discard them altogether. Okay, so another popular heuristic is diversity, which is trying to complement this difficulty. And the core idea is to select samples that collectively cover a broad range of data distribution. But the challenge is that it ignores the informativeness of a sample. So a natural idea is that how about we combine difficulty with diversity? But the challenge is really how to balance these two scores. Okay, so that leads us to the third data selection criteria, counterfactual-based selection. The core idea is that we want to evaluate the impact of a data point on the performance by hypothetically remove it and measure the resulting model performance change. We want to look at if we remove the data point, how much the performance changes. And we want to prioritize those data points with larger impact. The intuition is that if removing a data point significantly worsens the model's performance, then we want to keep it. It's a valuable data point. So if you compare this data selection strategy with difficulty and diversity, selecting data that concretely improve the performance has a more direct link to our ultimate objective of maximizing the performance. So it has a better and tighter connection to maximizing the performance. And central to this counterfactual-based selection is this notion of leave-one-out arrow, which I denote as LOO here. So the leave-one arrow basically calculates how much the validation loss at Z val changes if you remove your data, training data Z star, from your training data set D. And A here represents a learning algorithm. Okay, so everything is nicely formulated, but there is obvious challenge that you can't calculate the leave-one arrow very efficiently because you have to remove each data point kind of tentatively from your data set and retrain your model and see how much your performance changes. Okay, so there is a very well-known idea to the rescue, which is influence function. Influence function, so it is defined as follows. It is a validation gradient dot product with a training gradient modified by some Hessian inverse factor. Okay, I want to talk about how influence function is derived. Just want to highlight it is a local approximation to the leave-out arrow with assumption that this training algorithm has a strongly convex objective. you already maybe get a feeling that this influence function has some clear gap with how we currently train our foundation models. We almost never deal with a kind of strongly convex object function, but that's not it. That's not all the kind of challenge for influence function. I want to highlight a conceptual challenge of influence function, which is influence function does not account for the data order. So if you have two data points, identical data points, they will receive the same influence. But we all know that in current machine learning, even for the same data points entered at different time during the training process, they will have different impact. Let's dive in a little bit further. So right now, the foundation model training paradigms is usually single epoch pre-training. It has multiple stage curricula, pre-train, continue pre-train, fine-tune alignment, and so on and so forth. And we almost never train to convergence. So this means that a data point's influence may heavily depend on when it appears during training. Take this as an example. So let's say we have a training data point. Obama was born in Honolulu, and we use it in the first pre-training phase, and the model learns this fact. And in the second training phase, maybe we continue on training on some specific domain data, and accidentally the model forgets this fact. Okay, so this means that Z1 star, which is one of our training data, is forgotten. And we realize that, we want to correct this, and we, develop a third training phase where we add the same identical data point into this phase and make sure the model learns this fact again. Okay, so if you calculate influence function for Z1 star, which is used in the very beginning of your training, versus Z2 star, the same data point but enter in the later stage of the training. Influence function will give you the same score because it calculates the gradient only based on the final model checkpoint. But intuitively, this Z1 star is forgotten during the training process, so its influence is essentially 0. But Z2 star help you learn this fact, so it will have a much larger influence on the final model. How can we kind of accommodate this try to formulate a new notion of influence that can capture the complex of data influence and its dependency on the data order and timing? So that leads us to a new notion of leeward arrow. And the big idea of this notion is that we want to look at what's the impact of removing data for a specific training trajectory, not just the final model. Okay, specifically it is defined as follows. Again, this Z-val is a validation data point. We are looking at how the validation loss changes. So theta t here is a model if you train on everything keeping as is. And theta t prime is when you remove a training data point from the iteration that it enters into the training process. So in this case, it's TS. It calculates how the final model performance would change if you remove the data from the specific iteration it enters into the training. Pictorially, this is what happens. You remove the data, and you look at how the change propagates all the way to the final model, and look at how the loss changes at the final model. Okay, so you might get a feeling that this quantity is not easy to calculate. That's the truth. But there is a kind of theory establishing that it can be also approximated using some linear approximation. And you can see some familiar quantities here. You have the validation gradient, and you also have the training gradient. But here are some new bits, which is a big product of all the steps through which the training data's effect propagate all the way to the final model. Okay, you can see some Hessian terms in this product, meaning that the landscape, the curvature of the model in the intermediate steps really shapes how the data's impact propagate all the way to the final model. Okay, so again, you can see that it involves gradient, and Hessian is not easy to calculate, but the good news is that recent work makes this computation scalable to foundation model. Let's just see some empirical results with these efficient methods. So for the first time, you can look at how the training data influence actually evolves over time. And a very interesting phenomenon arises here is that it has a clear three-phase separation. At the very beginning, you'll find a very brief, high-impact region where the data has a lot of influence. And then the influence dips down, and you will have a more extended, low-impact basin, which is less responsive to data changes. And then the influence will grow kind of gradually back. Okay, so the big takeaway here is data influence is not static. It changes over time, and data from early and also mid to late stages are more impactful than other stages. Okay, so some of you might wonder like why you have this rise, fall, and rise pattern. I just want to give you some brief intuition about that. So data influence is somewhat determined by the gradient magnitude. If the gradient is large, you have larger influence. So initially, the gradient is very large, and so you have like kind of the influence is kind of driving by this force that is slowly decreasing. And it is a tug of war with another force. So because although the initial gradient is very large, but it is very far away from the final model, meaning that its impact and influence might be diluted during the process. So depending on when it enters the training process, so the kind of there is another kind of drive force, making the later data points actually having a higher impact. So overall, these two opposite forces will give you like this shape that is not monotonically changes. Okay, so this non-static influence actually points to a new frontier of data selection. In other words, you can actually, because the data influence is not static, and it has this clear face where the model is less influenced by the data. So this actually inspires a new idea for data selection. That means you can actually strategically invest your data selection-related compute across time. For those stages that are more influenced by data, maybe you can spend more compute to find the more high-quality data point. Whereas for those stages that is less responsive, maybe you can be sloppy about your data selection and to save compute. Okay, so this is just a pilot study of how we can improve data selection efficiently, kind of under the computation limits. So what is shown here on the y-axis is the perplexity reduction. Okay, the first column is no selection, so 0 baseline. Okay, the second column represents what happens if you select the data throughout the process. You can see that it can bring a big perplexity reduction. So what's interesting is this purple column. It represents what happens if you only select data in this initial high-impact region. Keep in mind that this impact region only accounts for less than 5% of your training process. But if you look at the perplexity reduction in comparison with what you can achieve selecting data throughout, it can achieve almost more than 50% of the reduction that can be achieved by always selecting the data during the process. And another interesting thing here is in the last column, we select data in those two high-impact regions, the initial region and the later region. The total length of these two regions is less than 50% of the training process. But if you only invest compute in these two regions, you can achieve a comparable performance or even better for some models to the performance that you can achieve by selecting data throughout. So this really shows the promise of kind of data selection in a dynamic way. All right, so let's recap this roadmap one last time. So we start with first principle, where we want to directly optimize the performance. We encounter two challenges. Search space. We first focus on these problem instances with relatively small space, and we talk about two big ideas to further cope with the complex objective, which eventually give us some principled practical algorithms. On the bottom, we have some truly kind of daunting, challenging problem with large search space, and we talk about some heuristics that can yield kind of strong results empirically. That concludes my talk. Thank you for your attention. I probably won't have time for questions, so maybe you can leave it to the end.
Okay. Let's just skip the break. So I'm Tianhao. I'm a first-year PhD student from Princeton. So in this part, I will present a unified framework for data selection algorithms and see how it can help us to better understand the current limitations and guide future directions. So first of all, why we need a unified framework for data selection? As we have seen, there are a lot of data selection techniques being developed. Having a common framework will help us to better understand, compare, and analyze the limitations and trade-offs between those methods and help us to guide the future work. So let's formalize our data selection problem first. In its most basic form, what we are trying to do is to find the best subset of our training data that will give us optimal model performance. So we start with a training set, and we have some way to measure how good it is. So that's our utility function, which we'll formally define in the next slide. So our goal is to find the optimal subset that will give us the highest utility value. So such an optimization problem typically comes with a cardinality constraint over the selected subset. This could be due to the computational constraint or other practical considerations, such as storage. So the utility function essentially tells us so if we train a machine learning model on subset S, then how good it is. So first, we take a training set and fit it into a learning algorithm. This could be gradient descent or any other learning algorithms that we are going to use. This gives us a trained model. Then we evaluate this model using some performance metric, which could be the test loss, classification accuracy, F1 score, or whatever makes sense for our specific task. So we start with our training set, apply our learning algorithm to get a trained model, evaluate it using our chosen metric, and get back with a utility score. So this utility score tells us how useful that particular data set is for our task. For example, one of the most widely used utility functions in the literature is the loss of the trained model or a test set. So here I just write one test point for simplicity. So by plugging in this specific utility function, we get the data selection problem formulation appeared in many papers that Ruoxi mentioned. So we're looking for the data subset that, when used for training, give us the best performance on our test point while staying within our size constraint. Data pruning is a closely related problem to data selection, but prioritizes different aspects. Given a training set D and a utility function, the data pruning aims to find the smallest possible subset that maintains the original dataset's utility. This problem is also known as a core set selection, with the goal of achieving data-efficient learning by removing redundant data points while preserving the model performance. So as a comparison, the data selection and the data pruning exchange their optimization objective and the constraint. So both approaches, they deal with the trade-off between the model performance and dataset size, but emphasize different aspects. However, in practice, maintaining the hard constraint on the utility is very challenging. Therefore, many data pruning algorithms actually focus on the optimizing the utility instead, which is essentially the same as data selection. So, as we discussed in the second part of the tutorial by Ruoxi, the nature of the utility function causes a significant challenge to the data selection problem. So first, our utility function usually does not have a nice tractable closed form expression, as it trains neural networks and evaluates their performance. So unless it's for super simple architectures like Continuous Neighbor, we don't know what the utility functions look like And it's often computationally heavy to query this utility function, but even just once. And secondly, even if we could efficiently evaluate the utility function, checking all possible subsets would be computationally infeasible due to the combinatorial nature of the problem. So those challenges motivate the need for efficient data selection. So we break down the general paradigm of data selection methods into 3 components. First, we need to choose an appropriate function class to model our utility function. For example, in offline data selection, the utility function is often being assumed to be a set function, while in online data selection or curricular learning literature, it is being treated as a more general sequence function. So what we need here is to restrict the possibilities of what our utility functions look like to make the data selection problem more tractable. Different kinds of the data selection methods have different underlying assumptions about the utility function class. For example, the popular scoring-based method, they assume the utility function is correlated with some additive utility function. So this reduces the problem to be estimating an importance score for each individual data point. After the utility function class being defined, the next step is to learn about the specific utility function we have from the available information that we have access to. So this is where the signal for data selection comes from. So popular choices in the existing literature include the geometric properties of the dataset, the statistics from the training dynamics, or model behavior. So based on those information, we hope we can get a good estimate and understanding for the specific utility function that we are aiming to optimize. For example, the scoring-based data selection literature, they use different types of the information we discussed about, in the second part of the tutorial by Ruoxi, such as the distance to the cluster center, the forgetting score, the gradient norm to estimate the importance score for each data point. Finally, we need efficient optimization problem. We need efficient optimization method to find the best data subset that given the estimated utility function. So, for example, for let's say that the feature distance, we choose the feature distance to the cluster center as the importance score for each data point. Then looking for the optimal subset is very trivial because we can just pick the top k data points with the highest score. So interestingly, this paradigm parallels with the pipeline of machine learning. So in machine learning, we choose the hypothesis class of the predictors and learn from the training data. And for data selection, we choose the hypothesis class of the utility function and learn from the available signals. Okay, so let's start with the most common constraint over the utility function class in many existing data selection literature, which is the input order independence of the utility function. So this means that we assume the order in which we present the data to our learning algorithm does not affect the final outcome. For example, even if we are trained with the SGD, where the model is trained on the data batch by batch, when the loss function is strongly convex and the model has been trained into convergence, then the final model as well as its utility is independent to the order of the training data we fit to the model. So under this assumption, our utility function only cares about which data points, which examples are being selected, regardless of their order. So, which essentially makes the utility function to be a multi-set function. And such a formulation makes the output of the data selection to be a data subset. So because right now, the utility function only cares about the membership, like whether a data point is being selected or not in this case. We can simplify and represent the utility function as a pseudo-Boolean function, where the input is a binary vector, where 1 means data point is being selected and 0 means we don't select it. So given this binary representation, we can further put more constraints over the function class where the utility function falls into. The simplest case is when the utility is positively correlated to some additive function. This leads to the most common scoring-based data selection method, where each data point's contribution can be evaluated independently. A richer function class is when the utility is correlated to some quadratic function, leading to the interaction-based approach. So this can additionally capture how the data points, how two data points interact with each other, like the redundant or complement to each other. Some modular functions are also popular choices in the literature, as they have elegant provable optimization guarantee by the greedy algorithm. So each of these choices, they represent different trade-offs between the expressiveness of the function class and the computational tractability. Let's look at the most common form of the utility function class being assumed in the literature, which is the correlation with the additive function. So if the utility function is being positively correlated with the sum of some scoring function applied to each individual data point, then the sum of individual scores increase. Our utility function also tends to increase as well. So this assumption is particularly powerful because it leads to a very simple data selection strategy, which is just assigning some scores to each data point and pick the K data points with the highest scores. So this transforms our complicated combinatorial optimization problem into a simple sorting problem. So for scoring-based data selection, each individual data point got a score based on some criteria, like a model uncertainty or gradient norm. So we then simply sort each example by the scores and select the top K. So the underlying assumption behind this type of the technique is that the sum of these data value scores across the data points in the dataset is a reliable indicator for that dataset's utility. So the scoring-based selection, they export different scoring functions for each individual point and hope that its summation should be correlated to the ground truth utility function. So under this simple structure, assumption of the utility function, we need to figure out like which exact scoring function we need to use that can better reflect the actual utility. So there are two kinds of the approach that being used in the literature, depending on whether representative validation data is available. So without the validation data, then we rely on the data difficulty measures as Ruoxi talked about earlier. So data difficulty-based scoring function, they assume that the scoring function based on so they determine the scoring function based on the difficulty of a data point for the model to learn. So we can organize those methods by the type of signals being used to evaluate the data difficulty. But when the validation data is available, then we can move beyond the difficulty measures to the data attribution method. So those methods directly measure each data point's contribution to the model performance on the validation set. So the key difference is that the attribution-based method, they use the validation data to get the ability to directly query the actual utility function, while the difficulty measures, they use some proxies that do not require such kind of like a representative validation data. So being able to directly query the actual utility function leads to the counterfactual-based approach that Ruoxi talked about in the last part of the slide, last part of the tutorial. Which include examples like a leave one out or input function, as well as the Shapley value. So after we obtain the corresponding scores for each data point, as we mentioned earlier, the optimization of this linear surrogate of the utility function is very simple, where we can just pick the data points with the top k value scores. So those scoring-based methods, they assume that each data point will contribute to the model training independently, regardless of which of other data points are also being selected. Okay, so now let's move on to a richer class of the utility functions that can further capture the pairwise interactions between data points. So this is by expanding from the additive to quadratic utility function class. So the key difference is that here we have an additional pairwise terms. So this additional pairwise interaction function, it captures like how two data points influence with each other in the model training, and is often being captured by heuristics like Fisher distance or gradient similarity in the literature. So this quadratic formulation, it significantly expands the function class beyond the simple scoring methods. For example, we can now express the scenarios where like similar data points, they might be redundant, which has a negative interaction, or the two data points might be complementary to each other, which has the positive interaction. So there's also a rich literature that assumes the utility function is correlated with quadratic utility functions class. One such example is a gradient matching based process selection. So it aims to select a subset of training data whose combined gradient match some target vector, like some target gradient as close as possible. For example, like this target gradient could be like the gradient sum of the gradient of the full training over the full training data, or the gradient in terms of some clean validation data that we have. So by expanding the mathematical formulation of this utility function objectives, then we can easily see that this is an interaction-based data selection, where the pairwise interaction is being captured by the gradient dot product. Another concrete example is the second-order infinite function. So the original first-order infinite function that Ruoxi talked about in the last part of the tutorial it captures the individual data point contribution. To model the interaction, we need to extend this to include more higher-order terms. So the interaction term here it involves more complicated computations with Hessian matrices. So this exemplifies a common pattern in interaction-based methods that we often need more sophisticated machinery to capture the pairwise relationships between data points. This increased complexity gives us more expressive power, but often comes at a greater computational cost. Also, for the interaction-based selection, the optimization problem becomes significantly more challenging. So unlike the scoring-based method, where we could simply sort and select the top k examples, this quadratic objective function is NP hard to optimize. To make this tractable, the greedy algorithm that iteratively select the data points to maximize the utility function gain is also been being used. Okay, so overall, when we move from the scoring to interaction-based method, we are trading the simplicity for expressiveness. So we get a richer function class expressivity, allowing us to capture more complicated relationships and potentially align better with the actual model training. However, obtaining the signals to learn such a quadratic utility function can often be much more expensive. And finally, the optimization is also be much more challenging. Okay, so now let's consider relax the assumption of the utility function being order independent, and instead being a sequence function. So the data selection problem is no longer aimed to select a data subset, but a data sequence. So the new networks, they are trained sequentially, batch by batch. And furthermore, the training paradigm of foundation models are unique. In the sense that they rarely train to converge, and they often just use just one epoch for the pre-training. And they typically go through multiple stages of the training processes, like the continual pre-training, fine-tuning, alignment, as Ruoxi just talked about. So even by training on the same data set with different orderings, they can lead to very different model performance. So assuming our utility function is order independent rather than a sequence function, it does not align well with the reality of for the foundation models, especially for the it does not align well with the deep learning, and which is especially for the foundation models that we work with. So to formalize this sequence-dependent behavior, we need to reformulate our utility function to work with the sequences rather than sets. This formulation simultaneously optimizes both which data points to include as well as their ordering. So optimizing over all possible sequences is, of course, intractable. Since the deep learning models are trained batch by batch, many data selection algorithms, they use the greedy optimization that builds the sequence one batch at a time, which corresponds to the online batch selection technique. This makes the optimization tractable while also captures the sequential nature of the deep learning. So the key insight is that for online batch selection, in each step, it optimizes the so-called this per iteration utility function. For example, at certain training iteration, we measure the utility gain of a candidate batch S by looking at the validation loss improvement after one grading step. Importantly, while the overall utility is order dependent, this per iteration utility function, it only depends on the current model state, making it order independent within each step. So the core challenge in online batch selection becomes like how to select the optimal batch for each gradient update. And we want to find the batch that maximizes our per iteration utility gain. So just as our offline data selection method, we can place different kinds of constraints on the function class over this per iteration utility function. So, for example, if we assume that it correlates with some additive function, so we get the scoring-based online selection, which is similar to our offline scoring method, but updated. But the score is being updated dynamically. If we allow for the quadratic terms, then we can additionally capture the interactions between examples within our batch. So many of the such approaches that we mentioned, mentioned in the second part of the tutorial by Ruoxi fall into this category, like the arbitrary loss or gradient-based online selection. So recall that in offline selection, that we assume the utility of a data set is correlated with the sum of individual data point scores. So this is straightforward. But evaluates the utility, but it evaluates the utility based on the final model performance after the complete training. And as a comparison, the online selection, they look at the marginal improvement, where the scoring function is time dependent, and the value of each data point can change based on the current model state. So in other words, the offline approach, they make assumption about the entire training process, and online selection puts a much weaker constraint by only consider just making assumption for just one grading step, which means that it is more flexible and align better with the actual utility function. However, the online batch selection requires performing the data selection for thousands of times throughout the training, which can often lead to prohibitive computational overhead. So therefore, in most of the literature, the data selection is actually performed periodically instead of for every iteration. And the selection is not over the full training set, but a much smaller candidate pool, as discussed in the last part of the tutorial. So overall, when we expand the utility function from the multi-set to a sequence function, then we get more expressive power. So we can capture the order dependent effects that are crucial in the deep learning. And moving from the offline to online selection allow us to align better with the utility function. However, the online selection they usually require more computation compared with their offline counterpart. Okay, so far we only discussed the case where each input unit to the utility function is a single data point. However, as is mentioned in the last part, it can also be other units such as data source or individual token. So if we switch the selection unit to data source level selection, then we can significantly reduce the decision space. So for data selection over the data source space, instead of making the hard selection decisions, the literature usually reformulates the problem as finding the optimal probability distribution over our data sources. So here the utility function will take as input as a probability vector representing the proportion of our data set sample from each of the available data source. The sequence function counterpart, where the distribution over data sources can change over time, and so for this case, like it can also be defined like in a similar way, which leads to the online data source selection algorithm. So we can similarly categorize the existing data source mixing method according to the function class constraints. For example, like analog to the scoring-based data selection method, many offline and online data mixing techniques, they assume the utility is correlated with a linear function of the probability vector, which captures many existing literature. Okay, so now we have a unified framework for data selection. How can we use it to analyze the existing algorithms? So here we study the most popular scoring-based method, and more specifically we study the data attribution method belongs to that. So in this category includes the examples like L score or input function or and the Shapley value. So here we need to recall the definition of the data Shapley. So this data Shapley is generally considered as a principled theoretically grounded way to quantify the training data importance. So it is well known that the Shapley value is the only solution concept that satisfies certain fundamental axioms in the game theory. So mathematically, unlike the Liouville score, the Shapley value considers the counterfactual performance change when adding the data point of interest to all possible data subsets, and then take a weighted average rate. So this makes the Shapley value being considered as a more reliable data attribution method compared with the Liouville score. So the data selection is generally considered as a standard downstream application of data Shapley, where the relevant experiments can trace back to the original data Shapley paper. So compared to other scoring-based data attribution method, the Shapley value is it is directly derived from the counterfactual analysis across all possible data sets. Therefore, the expectation is that using data Shapley scores to select a high-quality data set can lead to better performing models. However, this empirical results for the data sharpness effectiveness has been very inconsistent across the literature. So some studies, they report that the data sharpness can significantly outperform the random baseline, while others find that its performance is no better than the random baseline. So here we investigate the effectiveness of data sharpness in facilitating the utility comparison for different data sets. So that is, we formulate the performance on utility comparison as a hypothesis testing problem. So basically, like given two data sets and the exact sharpness value for each individual data point, we would like to guess which data set's utility, which data set's utility will be higher based on the sharpness value scores for each individual data point. So based on this utility comparison framework, we can show a crucial limitation in using the sharpness value for comparing the data set utilities. Without the specific structural assumptions about the utility function, any algorithms for utility comparison based on the sharpness values, they can be no more effective than the random guessing. So the intuition here is that for any of the two data sets and any given sharpness value scores, so there's always exist two different utility functions where the utility comparison of the two data sets are different, but they yield exactly the same sharpness value. So therefore, without any additional information about the underlying utility function, the practitioners cannot reliably predict the utility comparison between the two data sets based on the sharpness value in the information theoretic sense. And furthermore, the same result extends to a wide range of the data attribution techniques, and specifically all of the summary values with some mild structural properties, includes the famous Lewin score or the influence function. So the reason here is that the computation of the sharpness values, it transforms the utility function, which we can view it as a vector of a dimension 2 to the n, into the sharpness value of each data point, which is a vector of dimension n. So this transformation is not injective, and it has a very large null space, which allows for tons of the utility functions that use the identical sharpness value. So we have shown that the data sharpness can work absolutely bad for data selection tasks when there are no restrictions over the utility function. So the positive result here, however, is that when the utility functions are being confined to certain structures shaped by the properties of the underlying data sets or linear algorithms, then in this case, we can rule out those other possibilities, and the data sharpness can be much more effective in selecting the high-quality data set. So we show that when the utility function is positively correlated to the summation of some scoring function, which is exactly the same as the underlying assumption for scoring-based data selection, then the data sharpness effectiveness in data selection is optimal. So the proof is very simple. It's based on the observation that the data sharpness scores preserves the data value ranking of whatever actual scoring function is. So this preservation of ranking means that when selecting the data points with the highest sharpness value, it will be aligned with selecting those with the highest actual data value scores. So thereby optimizing the data selection process. Okay, so to summarize, if the linearity correlation assumption holds for the actual utility function, then the data sharpness is indeed optimal. But if the assumption breaks, then there is completely no guarantee that what will happen. Okay, so having seen the fundamental limitation, now let's discuss the potential future works. Okay, so as we can see that the utility function optimization framework, they illustrate fundamental trade-offs among different types of the data selection method. Assuming a too simple utility function class like linearity, it may fundamentally limit the data selection performance, as we just seen. However, expanding the space of utility function class, it may increase the cost of the learning and optimizing the utility function. So a fundamental question that remains under studies is what is the true nature of the utility function for deep learning, and particularly for the foundation models. So as is mentioned in the last part of the tutorial, that there are already some existing efforts in studying the scaling law for data source mixing. And for the utility function defined over the more fine-grained unit, like the sample, the data point level. So can we at least obtain some insights into its properties? For example, most of the methods so far, they only consider up to the pairwise interactions between data points. Which is essentially treating the utility function as a quadratic function. So that the third or even higher order interaction is indeed small enough that we can safely ignore them in the data selection. So this is unclear. Another issue that we can see here is that existing techniques use a variety of the signals to study this utility function, and a lot of them will require the model training. So far, in this formulation of the data selection problem, we just put a canonical constraint over the selected data set, which is usually determined by the computation cost or storage cost on the selected data set. However, a more complete formulation that directly addresses these computational constraints is to consider both the computational cost over the selected data set as well as the cost for the for doing the data selection. So, in other words, we are working with a total compute budget that needs to accommodate both the selection and training cost. So a few studies already show that different dataset size constraints or compute budget can lead to different optimal data selection method. So in practice, given a compute constraint, can we decide which data selection technique to use? So such a problem is not easy because it also concerns with the trade-offs of the data selection cost and model training cost. So we might need to deal with some question like for a fixed data selection technique, can we develop scaling law that maps the cost of the data selection to the resulting model performance utility? Another thing is that, as we discussed today, so the utility function for foundation models greatly depends on the data ordering, and it's more reasonable to treat it as a sequence function. So far, for the data sequence selection problem, most of the techniques are online data selection. However, is it the best we can do? So the online data selection is essentially like using greedy algorithm to optimize the utility function. But greedy algorithms can get stuck in the local optima. So if we only select the best batch for the next iteration, we might miss the opportunity for better long-term performance. And furthermore, the online data selection often requires modifying the implementation of the training loops, which may not be feasible in certain scenarios. So this raises an interesting question that can we do anything better than the greedy optimization? So this data sequence selection problem or curriculum learning has much fewer studies so far compared with data subset selection, and might have more opportunities to exploit. Okay, so this concludes my part and the entire tutorial. Yeah, so please feel free to ask questions, including any additional questions for the first two parts of the tutorial for Louis and Ruoxi. Do you two want to come here as well?
Thank you for the very comprehensive coverage of this topic. I just have one question regarding the offline method. So if my understanding is correct, the both online and offline referring to using the same model to do both data selection and training, right? So in this case, is both can be classified as a on-policy type of a selection. Is that correct?
What policy type of the selection?
So in this case, if we're using the same model for data selection as well as training, we are like using the same data selection result to train the same model. Is that correct?
Yeah, we are using the same data selection result to train the model. I mean, in the most basic form, but in practice, if some offline data selection algorithms itself, they also need to train the model as well. So sometimes to reduce computational costs and we will leverage techniques like proxy models. So in that case, it will be like a different. It will be like a use like a data selection result from another model, another smaller model to train the bigger model.
Oh yeah, exactly. That's what I want to ask. So based on your experience, do you think that's promising? Because there are hypotheses that the model that is not trained with the same data will have a different preference for the data set.
Yes, yeah. Actually, in Ruoxi's slides, she also shows some potential issues of this proxy model techniques, where if you train so if you train a bunch of small models and get the utility and fit a scaling law, for the models in the much larger scales, then the predictions will be much worse. Yeah. So one open question is how to select the best proxy model so that there can be the data selection results can have the strongest transferability across the model scales.
Right. Do you have also studies that shows up to what level that this kind of a proxy model results will be able to generalize?
Yeah, maybe I can quickly comment on your question. So there is one paper, not from none of us, but it shows that it's not the case that the larger model the proxy is, the better the approximation is. So in general, there isn't a clear trend about how to design the best proxy model. So both smaller model and bigger models may not have a good transferability with the target model that you are interested in. So in general, this space is not very clear and really see any conclusive evidence that the bigger proxy model is a better transferability.
Thank you very much.
Thank you.
Thank you for a wonderful tutorial. I enjoyed all three sections. Wanted to ask about the mixture weight optimization in section 2. Did I get it right that you have to, the fundamental assumption is that the data sets are independently affecting the final outcome? How realistic is that and how do you get around it?
Yeah, that's a great question. So, in fact, the theoretical results, the scaling results that I talk about, doesn't have to assume that each domains are independent of each other. As long as the data set, the aggregation of all domains can be decomposed of some independent skills. You can think of maybe like Common Crawl, Wikipedia, although like they heavily maybe depend on each other because they have like overlapping content, but as long as they can be decomposed into some dependent skills like coding, mathematics. So as long as these skills are roughly independent, you will have the same scaling law for the optimal mixture. So the assumption can be relaxed. Whether or not the data is truly decomposable to independent skills, I mean, that requires further study. Yeah, great question.
Is there a test for independence that you could do to understand if your data sets are truly independent, or it's mostly based on?
Yeah, of course, yeah. So basically, like you can just like train the actual, you can actually train the model and then like see like how different like the difference of between the scaling laws that you learned and are indeed like match we see the ground truth.
Gotcha. So if it's only affecting one skill in the ablation or different set of skills, disjoint set of skills, then okay.
So I want to highlight that even with these assumptions, the predicted weights works much better than just some heuristic way of defining weights. So which means that this assumption has some like value, but whether it really holds or not, it's like up to like further study.
Yeah, and also like it is possible to like extend that to like the linear assumption to like the quadratic functions, as we can see have seen like for the point level selection. So the issue is that like so suppose that you have like m domains and like for linear for a linear model to fit a linear model, then like you only have like m parameters. But like for like quadratic functions, then like you have like m squared plus m parameters to fit. So which means that like okay, so maybe like this ground truth is like this is align better with the ground truth. The computer cost that you need to fit such a scaling law, it will be like much higher. And if you do not have that much of the compute, then potentially like you will fit a very very poor scaling law, even if you also include the higher order term.
Thank you.
Yeah, thank you very, very much for giving the tutorial. I had a question about something that I think was missing, which was why was there so little discussion on submodular approaches for data subset selection? Because it seems like that actually satisfies and already has solutions for many of the future work that you say is important. For example, things like higher order interaction and interesting budgets and interesting constraints and fast scalable algorithms and extensions to non-submodular functions like difference of submodular functions. And there's also been a lot of work in data subset selection over the past 15 years that I think there, sort of fits into some of the things that you were saying was necessary for the future. And so in some sense, maybe the past maybe the future can be found in the past.
Yeah, the reason that I did not discuss it is because it's the time is too constrained. Yeah, so sorry about that if that upset you. Yeah, so and also like as you you mentioned that like so you mentioned that like this could be like the submodular function. It is just not clear that like whether the actual relief function is like indeed like a match with like it's actually can be approximated by a submodular function. And also
I think it is clear because, for example, when you say things like a quadratic function, I mean that's a very easy difference of submodular functions. I mean, you have the supermodular part and the submodular part, and so you can just add them together and you get but then you can actually have more general higher order interactions with differences of non-pairwise submodular functions, so that you get extensions of quadratic. So if you mention quadratic, then it seems like you should mention higher, things that can already do the higher order interactions that you're saying are necessary for the future.
Sure. Yeah. However, like I think like to maintain like the modular functions like optimization guarantee, like typically you still need to assume the monotonicity. Yeah. So this is like this already like not aligning very well with the model training.
Yeah, I didn't understand that last point.
So I did not like include like the modular function like in the roadmap because like the time is like a big constraint, and like the quadratic function is like much more accessible to the audience. We can add that like later for in the roadmap. We'll publish like all of the materials and slides after the tutorial.
Okay, thanks.
Yeah, thanks.
Yeah, hi. Thanks for the great talk. So I work on generalization and robustness. So I'm more curious how data selection, data pruning helps generalization or downstream tasks, and if there are works that try to study how data selection can help improve or degrade adversarial robustness. So any thoughts on that?
Yeah, this is a great question. I mean, so I ended up working on all of this data stuff because I studied adversarial robustness and out-distribution generalization before this. So basically, a couple of years ago, collaborators and I and others in the community built a lot of out-of-distribution test sets, and we were wondering, okay, what does best on these OOD test sets? And it seemed like the only thing that really moved the needle there was training on better pre-training data sets. Specifically, the CLIP model made a lot of progress on out-of-distribution data sets like ImageNet V2, ObjectNet, ImageNet R, ImageNet Sketch, and so on. So now, okay, good. So this motivated me to do all of this data work. Maybe now the question is like looking back, sort of like what have we learned? And I think it's still quite hard to design these data sets in a very goal-directed way. So we can make the numbers go up, but I can't tell you exactly on which of the OLD test sets they will go up more. And if anything, they go up roughly by the same amount everywhere. So we've studied this a lot. If you can look up a paper called Accuracy on the Line on this phenomenon. I'm also happy to chat about it later. The other aspect that you mentioned with adversarial robustness, I think data also plays a key role there, or at least having a lot of it. So specifically, right, if we go back to when people started studying this a lot in the setting of CIFAR 10 and ImageNet, there is a nice leaderboard on Robust Bench online. And currently, the best method is doing adversarial training with a ton of synthetic data. I think on the order of like 50 million images coming out of the Fusion model. And so for a comparison point, 50 million images, CIFAR 10 training set is 50,000 data points. And so I think this is like, or at least this makes sense to me from the perspective that you can show in simple sort of like theoretical models that being adversarially robust requires more data. Again, happy to chat more offline. There's a couple of papers that try to make this more concrete. But yes, I do believe that for robust generalization, data is very much key. And this is what brought me here, so to speak.
Okay, thank you.
Thanks for the great talks, folks. My question pertains to pre-training. So much of what we're trying to optimize with these different data filtering interventions are like benchmark performance of overall capabilities. However, sometimes our models are really good at things that we don't want them to be good at. Maybe they're really good at being toxic in some settings. So we might want to be removing data from our pre-training. Simple heuristics like not taking content from known unsafe websites make sense. But are there any similarly rigorous evaluations as to maybe safety or fairness interventions at the pre-training stage?
Yeah, great question. So I can tell you in the context of datacom for CLIP, for multimodal models, which I briefly touched on, we do have some of the benchmarks in our benchmark suite that specifically target, for instance, generalization across geographic regions. So there's a nice data set from Olga Rusakowski's group at Princeton, GeoD, Geographic Diversity, And you can basically see, okay, like is geographic diversity a metric that behaves similarly or differently from the other metrics that we target, like ImageNet accuracy and so on. And so far what we have found is that, fortunately, as long as you make the ImageNet numbers better, the GOD numbers also go up. So this is so far at least empirically the case that making the models better makes them better more broadly. Of course, this is not guaranteed, and it's important that we always benchmark this thoroughly. We've also done some evaluations on this in the context of datacom for language models. This is a partial answer. Maybe there's some specific aspect that you're particularly curious about?
Certainly a very broad topic, but maybe I'm thinking about, we do a lot of safety in post-training with language models about maybe not exhibiting a certain bias as a canonical example. Is there any work studying since post-training can be subverted by adversaries or in OD settings going to the source?
Yeah, no, I think this is a really great question. For instance, I mean, yeah, there's a good question of if you want your model to not do certain things, for certain things, probably you just want completely to erase that knowledge in pre-training, so the model is completely not aware of it. For certain other things, maybe the model should know what the bad thing is, so you can tell it more explicitly this is bad behavior. It has seen some examples of this and can distinguish that then later at test time. Yeah, for instance, I mean, okay, one concern that people have around language models as they get more powerful is that maybe they're going to be able to help you design a bioweapon. And so, like, is there certain sort of bioweapon-specific knowledge that we could very precisely remove in pre-training? I think this is a great research question. Having like good evaluations for this and then sort of like setting this up as a benchmark and seeing, okay, what exactly should we take out? So it's still helpful for biology researchers, but not for like bad applications.
Thank you.
Hi, thanks for the great tutorial sessions. I think when Professor Ruoxi talked about the online batching data selection, it reminds me of active learning literatures. So I was curious, since this talk didn't mention any active learning, literature, I just want to, is there any fundamental differences, or just want to know your perspective on that?
I would say a lot of the data selection strategies I discussed have a very tight connection with active learning. For example, the difficulty-based scoring method, a lot of them like borrows intuition from active learning, where we try to select the most uncertain samples. It's just that uncertainty is characterized differently in language modeling, so maybe you want to use alternative metrics to measure uncertainty. And also, active learning, you really use diversity sampling. A lot of those techniques are still applicable in the foundation model context. It's just like how you implement it and adapt to this specific like modeling and data format. So I would say, yeah, so like there are a lot of amazing inspirations and like gems in active learning. And I already see a lot of papers that try to kind of using similar ideas in the foundation model training context, like diversity sampling or like difficulty-based scoring. So a lot of them are applied in foundation model errors too.
Okay, thank you.
So great question. So I just want to add that. So for active learning, because like it's typically like dealing with the unlabeled data. So when for each round, when you select the data, you need to send it to a human labeler. So this is an additional cost compared with like you directly like sample the labeled data. So like basically like basically, like for the constraints that like you need to be put on the like in the data selection, you should account for like both you basically like you need to additionally account for the cost for like labeling it. Like if you send to the human labeler, you need to pay him and spend some time. He has some turnaround time to get the label back to you. So this is like another kind of like cost for like the active learning. Yeah, I mean, like in terms of like problem formulation and constraints.
Okay, thank you.
Cool. I think we are out of time now. Sorry about it. I saw there's maybe one more question, but it's 4:04, and I'm not sure if someone else is in this room right after us. Does someone know? Yes, looks like it. Okay, sorry about that. So thanks everyone again for coming. and we'll be outside the room for more questions. See you everyone, bye.